Okay, f prime of negative 1 is 0, yes. The second derivative at negative 1 is greater than 0. F of negative 1 is negative 5. F prime of 7 is 0. F double prime of 7 is less than 0. F of 7 equals 10. The second derivative at 3 is 0. And F of 3 is 2. That's a mess. Good pick. So let me check what I copied. F prime of negative 1, F double prime of negative 1, F of negative 1 is negative 5, F prime of 7 is 0, correct. F double prime of 7 is 0, is less than 0, yes. F of 7 is 10, F prime of 3 is 0, and F of 3 is 2. Perfect. This is a summary of everything we studied in this chapter. Okay. Can I graph this? No. Not before I summarize all my information in the table. F prime, f of x. I don't even know where to start, where to look. This is all over the place. So the second derivative. I hope you agree. Okay, so then negative infinity to infinity. And let's take it slowly. I would like to start with this. At negative 1 is negative 5. Don't erase it like that. I'm just making a point. F of 3 is 2. Done. F of 7 is 10. Okay, done. F prime of negative 1 is 0. Done. F prime of 7 is 0. Done. F double prime of negative 1 is positive. F double prime of 7 is negative. The second derivative at 3 is 0. So at this point, I have all the information summarized, but let's discuss it first before we go ahead and graph an example. So when the second derivative is positive, what can we say about the function?
Concave.
Up.
Up.
What does it mean then that negative 1 comma negative 5, when the function is concave up and the derivative is 0? What type of point is negative 1 comma negative 5?
A relative minimum.
Excellent. So we established that negative 1, negative 5 must be a relative minimum. Awesome. That's all this is saying to us. Okay, let's jump here. When the second derivative is negative, what do we know about the function?
It's concave down.
Good. What type of point is 7 comma 10, knowing that the derivative is 0? This is crucial. The derivative is 0. The function is
maximum.
That's a relative maximum. That's all this is saying. Done. So this is done. This is done. Now let's discuss that. And then we know what to do. See, here, this is positive and this is negative. And the second derivative is 0. And it changes sign. What type of point is 3 comma 2?
Inflection point.
Inflection point. That's all that is saying to us. But that's gibberish. If I don't organize it and I don't analyze it and I don't see what is happening, it's gibberish to me. I will not be able to do anything with that. So this is a very good example why the table is so important. So now we can come up with any graph you want that fulfills the given conditions, and we can add on whatever else we want. It doesn't matter, as long as the given conditions are fulfilled. So let me see. We go to negative 5 and up to 10. Okay. Good pick. I enjoy this one. Okay, at -1 is -5. And it has a relative minimum. At 3 is 2, and that has to be an inflection point. And at 7, 3, 4, 5, 6, 7 is positive 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. So the function has a local minimum, comes to an inflection point, changes concavity. I'm done. It looked very difficult with all those pieces of information, but that's it. The relative minimum, the inflection point at 3, 2, because the second derivative changes sign and it's 0 at that point. And then it has a relative maximum, and the relative maximum is 10. The value where the maximum is 7. How much? 10. Where is the minimum? At -1. How much? -5. And the inflection point is here, where the function changes concavity from opening upward to opening downward. And that's it. Could we have done this without the table? I think not. Okay, let's take a look at, I wanted to look at a graph and analyze this. So rainfall in Reno. Okay, the average monthly rainfall in Reno, Nevada is approximately given by this function. R of t is the amount of rainfall in millimeters at t months since December. Okay, so t equals 0 means December. Okay, find the points of inflection for R. What is the significance of these points? So obviously, I have to perform some calculations, but obviously it opens down, so there must be an inflection point here because it changes concavity. And I don't think there is more than one, but we will look. So opening down, and all of a sudden, it changes concavity. So let's take a look. I'm going to copy 61. And this is R of t equals -0.006 t to the 4th plus 0.213 t cubed minus 1.702 t squared plus 0.615 t plus 27.745. Okay. In order to determine points of inflection, what do we need to do? We're not asked to graph. We're only asked to find points of inflection.
Take the second derivative.
Right, but first we have to go through the first derivative because we cannot jump directly. Very good. So then R prime, so 4, -0.024 t to the 3rd plus 0.639, make sure my numbers are okay, 639, yes, minus 3.404 t and plus 0.615. And now, only now, the second derivative. Let's take a look. 0.072 t squared plus, and I think that this is 1.278. Correct me if I'm wrong, please. -3.04. Good, so now we have to set this equal to 0. And I will also multiply both sides by -1 in one step. So 0.072 t squared minus 1.278 t plus 3.404 equals 0. I'm going to use my magic calculator. We can use the quadratic formula, of course. I just want to pass this because I like to move on to the next section. So I'm just going to go to second and poly, put 2, and copy the coefficients. 0.072. -1.278 and 3.404 and solve. So x1 appears to be 14.48 and x2 appears to be 3.26. So these are in months. Well, we cannot use 14. So let's take a look again at the graph. See, the maximum here is between 0 months in December and 12. So that's why I couldn't even see the second point of inflection. There is none. No second point of inflection. So this will be disconsidered because it's outside of the domain. The domain is 0 to 12, and this is 14, which is outside. So now, this is not enough. I cannot write here, this is an inflection point. No, no. I have to show that the second derivative changes sign at this point. So just saying, oh, this must be the inflection point is not enough. So I will write t between 0 and 12. I will write 3.26. I only need, in this case, the second derivative. I know it's 0. I will plug in 0, and I see it's negative. And I will plug in 12. I don't know what I get. Right? But I know that between the solutions, between this and 14, the function has to have the opposite sign of the leading coefficient. So if you plug in anything on this side, it has to be positive. Now I can say, since this second derivative is 0 at 3.26 months since December, and it changes sign at that point, guaranteed the inflection point is 3.26 r, comma, r of 3.26, which I did not determine yet. I have to plug it in. So this is the point of inflection, and it makes sense. We can go back. So at 3.26, as expected right here, there is an inflection point. And it also says, what is the significance of this point? So what does it mean? So the fact that the function changes concavity, right? So what can we say? Anyone would like to comment? What is the significance of that? So from the function from opening downward, and in other words, decreasing to
That's where it shifts.
That's where it shifts, correct. So from decreasing, all of a sudden it starts increasing. So this point has the maximum rate of change at this point, negative. So this slope here is 0, and then it increases in the negative sense, and then it goes back up to, it increases back to 0, and then increases. Okay, I would like us to continue. If you have any questions, please let me know. Any questions about how to create the table, how to graph a function? I know just 1 or 2 examples are not enough, but we move on to the next section in which we have rational functions, and we're going to practice the same thing again. So in the next section, we're talking about rational functions, the same idea, just graphing rational functions. And we're going to use the table, all the steps, but we're going to add something to it. So rational functions. Rational functions have something that polynomials do not have. They may have vertical asymptotes. They may have horizontal asymptotes. And they may have slant asymptotes. So a vertical asymptote is a line like this, of course. A horizontal is a line like this. What is a slant? Something like this. Or oblique. Not vertical, not horizontal. These do not exist at the same time. Never on one function. If a function has horizontal asymptote, it cannot have slant. If it's a rational function, I'm talking about rational. If it has a slant asymptote, it cannot have horizontal. This one goes with either one, or not at all. So these, the vertical asymptotes have no influence on the horizontal and slant. So now let's start. I'll let you choose. Page 231. Let's choose a rational function. 231. And use the table and just write everything. Do not choose slant asymptotes yet. I need to present that after we work on a couple of problems. And let me just say, the slant asymptotes are only for a function, rational function, with a degree n plus 1 in the denominator and degree n in the numerator and n in the denominator. Meaning the numerator has a degree by 1 unit higher than the denominator. So degree 3 over degree 2, degree 2 over degree 1. These are the only ones that have slant asymptotes.